Hello everybody, welcome to chapter 8. This unit is going to involve us having a look at graphs and networks. So it's going to take a little bit of our information that we've learned during our matrices unit and then move into networks. So what we're going to be looking at today is chapter 8.1, which is looking at introducing this topic. So the seven bridges of, and I can't pronounce that, is basically a really famous mathematical problem that involves seven bridges around a river and around a town. So it's basically you're going on a walk, you can cross each bridge, but you can only cross it once. And it was deemed impossible. So the problem was actually solved eventually. And the way that it was solved is using this network diagram. Okay, so a network is basically kind of like a graph, okay? So a network is a group of interconnected people or things. So we're looking at how things are actually connected. A graph is a diagram of a network, okay? So that's how we can represent the image, which has points that we call vertices, okay? So these corners are our vertices. So here we've got A, B, C, D, which are connected by lines called edges. So the line joining A and C is an edge, A joining B is an edge, B joining C is an edge, and C joining D is an edge. Basically, these can be then used and analysed. Okay, so we label our vertices with capital letters, and then the edges are referred to by the two vertices that are being joined in between. We also say that graphs can have faces. Okay, so a face is basically a region that's enclosed by three or more edges. Okay, so here A, B, C is enclosed, and that is considered a face. So if there is a region that's created by a loop or multiple edges, we don't count them as faces. The region outside the graph, so all of this space that's outside the graph, is also considered to be a face. Okay, so in this case, we've got the inside area that's enclosed and the outside area. So this would be deemed to have two faces on the right. This same graph that's over here, okay, we can draw it in a few different ways. Basically, the way that we're identifying it is how many connections are made from one letter to the next. So here, A to B has one connection. A to B has one connection. A to B has one connection. A to B, there's one connection. A to B, there's one connection. The same way here, we can see A to C, there's one connection. A to C, there's one. 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 Okay. C to D, there's one connection. C to D, C to D, C to D, C to D. Okay. And then, of course, our C to B. Oh, that should be in yellow. Our C to B can be shown, C to B can be shown, C to B can be shown, and C to B can be shown. Okay, so the same graph can be drawn in a few different ways, and it's important, the main bit here is which edges are connected to which vertices. So they may look very different to each other, but they actually all show the same information. When a graph shows the same information, we call this an isomorphic graph. Okay, so all of these graphs are isomorphic. All right, so just as a summary of the information that we've just spoken about, okay, your vertices are these corner points, edges are the lines that join vertices together. If to a vertice there are more than one edge joining the two, we can say that they are multiple edges. And of course, if there's one connection between a vertice to itself, we can call that a loop. The last one is an isolated vertex. So that's basically a vertex that's not connected to any other vertex. Okay. This bit here, the degree or order of vertex is basically the number of edges that are linked to that particular vertex. So if we look at this diagram here, the degree of A is 2. The degree of C is 1, 2, 3. Okay. Oh, where did we go? We just scrolled all the way down when we didn't need to. All right. This part here, the degree sum of a graph is basically the sum of all the degrees of all of the vertices. So basically the way that you can work it out is we can go degree sum equals 2 times whatever the number of edges are. Let's go through some examples. So here we have got a graph. Let's do part A, and we need to identify each of these components. So if we look at the first one, how many vertices are there? There is 1, 2, 3, 4, 5 vertices. Okay. If we look at isolated vertices, there's no isolated vertices, so we can say 0. The number of edges, we've got 1 edge, 2 edge, 3 edge, 4 edge, 5, 6, and 7. So there's 7 edges there. Faces, we've got 1 face, 2 face, 3 face, and remember the outside is also a face, so that'll be 4 faces. Loops, well, we don't have any loops because a loop is like this one in part B, so 0 loops. And vertices with even degrees, so we've got to look at the degrees of each of them. So let's look at each vertice and see how many degrees it has. So vertex H has 1, 2, 3. Oh, where's my pen gone? 1, 2, and 3, which means that is not even. 1, 2, 3, that is not even. 1, 2, yes. 1, 2, 3, 4, yes. 1, 2, yes. So it has 3 of its vertices with even degrees. And then pairs of vertices with multiple edges. Okay, so there are no pairs here that have multiple edges. So in this instance, we would do 2 times the number of edges for the degree sum instead. Okay, so here, where is the pen gone? There we go. We go 2 times the number of edges. The number of edges was 7, so our degree sum is going to be 14. All right, you would basically follow that exact same sequence for question B and question C as well. So if I just get rid of all of our working out that we've just done, let's have a look at the next one. So looking at part B, there are 1, 2, 3, 4, 5 vertices. There is 1 isolated vertice, or vertex, sorry. There are 1, 2, 3, 4, 5 edges. In terms of faces, okay, there is 1 face, okay, because this is all of the outside of the graph. Remember, loops or multiple region edges are not faces. So here we've only got the 1 face. There is 1 loop at B and vertice with even degrees. So again, I'm just going to get rid of all of my scribble so you can see exactly what I'm doing. Basically vertices with even degrees. So B is a 1, C is not, D is 2, E is 1, 2, 3, 4. Okay, so we've got 2 there with even degrees. The next bit, pair of vertices with multiple edges. Well, multiple edges can be seen with this one here, so C and D, and then, sorry, D and E, not C and D. And then the degree sum is again the formula 2 times by the number of edges, which is 5, equals 10. So the degree sum would be 10 in this instance. All right, for our final question over here, what we would do is maybe write this in a format that is a little bit easier to read. So because this graph has edges that intersect with one another, especially over here, but because there's no vertex at that point, redrawing this is going to be easier. So if we can redraw it into one of its other isomorphic versions, this is going to help us. So what we can do, so I'm going to draw my 4 vertices again, and I'm going to say H goes to F. So let's go H and F. H goes to F. F goes to A. F goes to A. Sorry, I'm just turning my thing off. All right. And then if we put T here, T goes to A and T also goes to H. And this is basically showing all of the same information. So how many vertices? We've got our 4 vertices. How many isolated vertices? Well, there's none. How many edges are there? Well, there's 4 edges. 1, 2, 3, 4. There are 2 faces. We've got one inside, one outside. There's no loops. There's all 4 vertices have even degrees. That's 2. That's 2. That one there is 2, and H is also 2. Okay, so all of them have even degrees. There's no multiple edges ones, and then the degree sum, we're going to go 2 times number of edges, which equals 8. All right, so this is basically analyzing graphs, and you can see all of the working out there for you as well. Next bit is about drawing graphs. So when drawing, it's basically really important to see which edges are connected to which vertices. This is the most important information. So you need to think about the different ways that you can get the information that we are after. So we need to sketch a network diagram representing the roads that are connecting the 4 towns A, B, C, D. Okay, so if we have a look here, this is the diagram that we've been given. We need to consider how many direct routes there actually are that are joining each of these here. So if we think from A to C, we've got 1 route, but we can also go this way. So there are 2 routes connecting A to C. If we look at A to B, well, there's only 1 way there. Okay. If we look at B to C, we can go this way. We can go this way, or we can go this way. There are 3 ways. And before this starts to get really messy, I'm going to scribble out my scribbles again, and we'll keep going for the next ones. So then we look at from B to D. Okay, I can go this way, or I can take this shortcut as well. So there are 2 ways. From C to D, I can go directly ahead, or I can take my little shortcut thing again. So there's 2. And then D to D, well, there is 1 way that I can get to it, because I can go from here, I can go all the way around again. So that's sort of forming a loop. So now that we've got how many connections are between each vertex, we need to be able to draw the network that's associated with it. So what I would do is I would start off by drawing my vertices. Okay, so I've drawn A, B, C, D, and then connect the vertices with the correct number of edges. Okay, so A to C was 2, so I would draw 1 line and then 1 more line. A to B was 1, so I'm just going to draw 1 line. B to C was 3, so we're going to go 1, 2, 3. B to D was 2, so we're going to go 1, 2. C to D was also 2, so we're going to go 1, 2, and then D to D is itself, so I'm going to go around, and you can see that this is exactly the same as this one over here. Have a go at doing 8.1, and if you need some support, leave a comment or send me an email.